This video is on Unit 8 on Trigonometry, Chapter 15, Right Triangle Trig, Lesson number 1, Intro to Trig. We're going to look first at the Pythagorean theorem. The Pythagorean theorem is used to find a side length on a right triangle. The formula is a squared plus b squared is equal to c squared, where a and b are your legs and c is the hypotenuse. In example number 1, the directions here are telling you to find the missing sides, give your answer in simplest radical form. Number 1, we've got the 4 and the 8, and I know that those are the legs because those are the two sides that make up that right angle. And then across from that right angle is always the hypotenuse. So setting this up, we've got 4 squared plus 8 squared is equal to c squared. So 16 plus 64 equals c squared. And that's going to be 80 equals c squared. Now, when we go to square root this, normally we would say the positive and the negative root, but it's not going to be the negative root because the c does represent the measure of the length of that right triangle. It's the hypotenuse. So we're going to simplify that. If I take 80, put it in y equal, divide by x squared, this is going to simplify to 4 times the square root of 5. So the measure of x is 4 times the square root of 5. I'm going to go ahead and work number 2 because it's slightly different. So in number 2, you are given the measure of the hypotenuse. So we're looking for x. So x squared plus 22 squared is equal to 24 squared. So x squared plus 484 is what 22 squared is. And then 24 squared is 576. So in this instance, what we have to do is subtract the 484, and we get x squared is equal to 92. And then when we square root both sides, again, you're going to simplify that radical, and x is equal to 2 times the square root of 23. Now let's look at 2 special cases. We've got special right triangles. So your 45, 45, 90 and your 30, 60, 90 are special right triangles. There are certain characteristics about the measures of their sides that occur over and over and over again. So in a 45, 45, 90, because the two angles are congruent, the sides opposite those two angles are also congruent, which are the legs of the right triangle. If I let one of them be x, then we know that the other side is also x. So the x is going to represent the measure of the legs of the 45, 45, 90. Now, what happens here, if you run that through the Pythagorean theorem, what's going to happen is the length of the hypotenuse is always going to be the length of one of those sides times the square root of 2. So if you can memorize these characteristics, then you can find the missing measures on any 45, 45, 90. For example, look at number 3. Number 3, we have a 45, 45, 90. The y represents the hypotenuse, so the 10 and the x represents the two congruent legs. Since 10 is one leg, x is also going to be 10. And then to find the measure of the hypotenuse, we're going to take that 10 and multiply it times the square root of 2. Now, I didn't have to do any math. I didn't have to do the Pythagorean theorem. All I did was apply the knowledge that I have about the characteristics of the sides of a 45, 45, 90. Looking at example number 5, we have the measure of the hypotenuse. And to go from the hypotenuse back to a leg, we're going to divide by the square root of 2. So if I take the 14, the length of the hypotenuse, and I divide by the square root of 2, we're going to get 14. And again, both sides are 14 because the legs in a 45, 45, 90 are congruent. Looking at example number 7, the 27 represents that long, actually, you know what, that's a 30, 60, 90. Let me jump to number 4. Number 4 is another 45, 45, 90. And 16 represents the hypotenuse. So to go from the hypotenuse to a leg, what we have to do is divide by the square root of 2. Now, we cannot leave this fraction looking like that because a radical is in the denominator. So what we have to do to fix this fraction is what is called rationalizing the denominator. To do that, you're going to multiply by the square root of 2 over the square root of 2. In the denominator, the square root of 2 times the square root of 2 is just 2. And in the numerator, 16 times the square root of 2 is not going to multiply. And then I can reduce the 2 and the 16. 2 goes into 16 8 times. So this one's a little more complicated, I'll say, than the others because you end up with a radical in the denominator, and it does make it a little more, where you have to think, but still doable. Looking at 30, 60, 90, I want to talk to you about this one next. So in a 30, 60, 90 right triangle, we're going to let the short leg, which is the leg across from the 30-degree angle, be x. So if you think about the short leg, that's always your x. The short leg and the hypotenuse are related. The hypotenuse is always 2 times that short leg. And then to get the long leg, you're going to take the short leg times the square root of 3. I'm not going to lie, the 30, 60, 90 right triangle is a little more complicated than the 45, 45, 90. But again, it's still doable. You just have to memorize the relationship in all of the sides. So let's start with example number 6. In example number 6, we know the measure of the hypotenuse. The measure of the hypotenuse is 8. The easy relationship is the hypotenuse and the short leg. And the short leg is always opposite that 30-degree angle. So we're going to take that 8 and we're going to cut that in half, and x would be 4. And if you know the short leg, you take that times the square root of 3 to get the long leg. And then let's look at example number 7. In example number 7, I have the measure of the long leg. So this is the one that's, I think, the most complicated. To go from the long leg, let's go back to that 30, 60, 90 right triangle. Looking at the long leg, it's x times the square root of 3. To go from the long leg to the short leg, we've got to divide by that square root of 3. So let's go back and let's take our 27 and let's divide by the square root of 3. Now again, you are not allowed to leave a radical in the denominator. So we need to fix this by multiplying by the square root of 3 over the square root of 3. We get 27 square root of 3 over 3. And then 3 is going to divide into 27 9 times, and we get 9 times the square root of 3. Now, that is the measure of the short leg. So that's going to be the y. Y is 9 times the square root of 3. To find x, which is the hypotenuse, we're going to take that short leg, and we're going to multiply by 2. So if I take 9 times the square root of 3 times 2, it's going to be 18 times the square root of 3. And then number 8, I think, is a little bit easier. Number 8, you've got the short leg. 5 times the square root of 6 is the short leg. We'll double that to get the hypotenuse. So 10 square root of 6 is going to be the x. And if I take 5 times the square root of 6 and I multiply by the square root of 3 to get the long leg, I get 5 times the square root of 18, which needs to be reduced. So that's going to simplify to 3 radical 2, and 3 times 5 is 15 radical 2. So all those rules of simplifying radicals are going to come back to haunt us. All right, let's keep going. The trig functions. A trigonometric function is a function whose rule is defined by a trigonometric ratio. A trigonometric ratio compares the lengths of 2 sides of the triangle. The Greek letter theta is used to represent measure of an acute angle in a right triangle. Sine theta is always going to be opposite over the length of the hypotenuse. So in this triangle over here to the left, if this is theta, the side opposite would be A. And the hypotenuse, remember the hypotenuse is easily identified because it's the side across from the right angle. Cosine is adjacent over hypotenuse. And in this triangle to the left, if this is theta, adjacent side is going to be the side that helps make up theta, which is B, divided by the hypotenuse, which is C. And then tangent is opposite over adjacent. And again, your opposite side is the A, and the adjacent side is the B. You are introduced to two more trig functions here in Algebra 2, cosecant, secant, and cotangent. And they're lined up in their reciprocals. So sine and cosecant are reciprocal functions. So cosecant is going to be your hypotenuse over the opposite. And then cosine and secant are reciprocal functions. And since cosine is adjacent over hypotenuse, cosecant is hypotenuse over adjacent. And then for cotangent, it's the reciprocal of tangent. So since tangent is opposite over adjacent, cotangent is adjacent over opposite. And we're going to get comfortable with these. So let's look at example number 9. Number 9 says, find all 6 trig ratios for theta shown in the triangle below. Well, in order to do this, we need all side measures. And in this triangle, I only have 2 legs. So we need to use our Pythagorean theorem to find the length of the hypotenuse. So 16 squared plus 30 squared is equal to c squared. So 256 plus 900 equals c squared. That's going to give me 1156. And then we're going to square root, and we get c equals 34. So the length of the hypotenuse is 34. So remember from your trig functions, sine is opposite over hypotenuse. So the opposite from theta, here's theta, the opposite side is 16. Your hypotenuse is 34. And then we need to reduce that. 16 over 34 is going to reduce to 8/17. That's a 17. Your cosine is adjacent over hypotenuse. And adjacent side from theta is going to be your 30. Again, the hypotenuse is 34. Reduce, and you get 15/17. And then for tangent, it's opposite over adjacent. So 16 over the 30, which is going to reduce to 8/15. Now, if you have the sine, cosine, and tangent, it's very easy to get the cosecant, secant, cotangent. The cosecant is going to be the reciprocal of sine, so 17 over 8. Secant is the reciprocal for cosine, so 17 over 15. And cotangent is the reciprocal to tangent, so just flip that fraction. And that's how that's done. I want to jump down to trig ratios of special right triangles. Angles of 30, 60, and 45 are used frequently in trigonometry. You can use your knowledge of the side relationships in special right triangles to find the values of the trig ratios. So I'm going to fill in your 45, 45, 90 with x, and x times the square root of 2. So if I want the sine of 45, pick a 45, it doesn't matter. Sine is opposite over hypotenuse, so this would be x over x times the square root of 2. The x's are going to cancel. And then we got to multiply by the square root of 2 over the square root of 2. Can't leave a radical in the bottom. So we have radical 2 over 2. And that is a very common theme. The sine of a 45-degree angle is the square root of 2 over 2. Let me do a 30 real quick. Sine of 30. Remember, in a 30, 60, 90 right triangle, the 30-degree angle gives you your short leg. That's my x. The hypotenuse is 2 times that. And the long leg is the x times the square root of 3. So if, say, I wanted the sine of 30. So coming from that 30-degree angle, the sine is opposite over hypotenuse. So I'm going to take the side opposite, which is x, and divide by the hypotenuse, which is 2x, and I get 1/2. So that's how that works. Again, if you know those ratios, you know those special sides of those right triangles, finding these becomes a lot easier. So those are your notes for Chapter 15, Lesson number 1, Intro to Trigonometry.